Here we go. Okay, everyone is more or less back from the midterms. Presume that we're all feeling a little bit of dazed, a little bit stretched to the limits. So I suggest we take it a little bit slow today, just recover a little. And I want to just preface with saying that we have covered the bulk of what is needed for this course. Okay, and so in a way of saying that all the techniques, everything that we need to really, or most of the things that we need to do in terms of the theoretical aspects have actually been done. I told you before. Um, the electromagnetic fields are simply governed by Maxwell's equations. So there isn't really much to it other than now practicing, right? How to solve boundary value problems, how to recognize, you know, what boundary conditions to use, and how to get the relevant fields. So, hopefully now we've kind of covered most of it. Things will slow down a little, and the rest of it is really just about practice. Okay. Now before I really get started, let's get some matter of administration out of the way as well. We have coming Thursday, we're gonna do the course evaluation. So let me quickly bring up the details. So on Thursday, we will set some time apart, probably at the end of the lecture. I'm going to set some time apart to do the course evaluation. During the, I'll give you 10, 15 minutes at the end to do it. And you should be emailed the links to the survey. So each of you will get individual emails with links to the survey, and there you can submit your CTE survey, and then you can express your opinions there. Right, the total period will be there. The link will be available for a day, but as I said before, I'll also give you some time during the lecture at the end to fill in the scores. Okay, so that's gonna be up for Thursday. But for now, let's do the fun stuff, and let's take a look at electromagnetic fields in matter. Okay, so this topic is, it seems very tricky, right? Because we end up in scenarios where we can have different materials stacked up on top of each other. We have to take a look at different interfaces. But if you simply start with the basics, I believe things could be made reasonably insightful and reasonably straightforward. So let's start this part with an actual recap. Okay, so what we basically did last time around is we looked at what happens, or how can I describe a material that has some polarization or some magnetization. Okay? So in particular, we're talking about some material here that in some region here, it has either some P, some polarization, or some M, some magnetization. We talked last time about different ways. So either in the dielectric case, where we have the electric field polarizing the atoms, the molecules, right? It stretches apart, or you can end up with something that has a natural dipole moment and you end up turning the dipole moment aligned with the actual field. So those are ways in which you can polarize a dielectric, which is, compared to a conductor where the electrons are completely free to move. So as soon as you put a field there, you end up with just some surface charges left, right. Now for the magnetic case, again, we show two different examples where we can either align the magnetic moment along some magnetic field that is in a magnetized material, or we gave a very classical example where we slowed down or sped up the orbits depending on the field. Now, I want to stress, right? These are just toy examples. In order to get a full treatment, especially for the magnetized materials, we do need to look into quantum mechanical effects. And when we look at ferromagnetism, which is at the end of this chapter, we will look at one example of these quantum mechanical effects. But for the time being here, we only concern ourselves with electromagnetic fields and the macroscopic behavior. And so we take more or less a kind of a broad, kind of macroscopic, macroscopic picture. Okay. Now, in terms of the actual the mathematics behind it, it was fairly straightforward. So we looked at material where we have three scales now. We first look at R, which is where we want to evaluate the electromagnetic field. And then, of course, we have, have some, let's do this one. We have some scale where we look at, okay, which element, volume element I'm considering. And then finally, we have another scale here, denoting it with double prime, where I want to take a look at some volume so that I can average out the properties, either the polarization or the magnetization for this field. And so last time around we looked at how to write down the scalar potential and the vector potential in a relevant way. So in just to recap again, here is the scalar potential. It's just Ke and the sum of all the j's, where j in this case is all the different elements here and here. And then, of course, integrating over the volume of this. And here's rho. And then, of course, the distance prime minus r prime j here. And then integrating over this, okay, over that entire little volume. Again, similarly for the vector potential, I can just write Km, again, the sum over all these little volume elements, and then the integral to take the average of these volume elements. And now here we have the current, R double prime, dp double prime j, and then divided by R minus R prime minus R double prime. Let's label these with J. Okay, and so again, like we did before, when we want to evaluate the leading order contributions, we end up doing a multiple expansion, where in this case now, because we have three different scales, we first start off with evaluating this R prime, sorry, this R minus R prime minus R double prime. That is just, in an expansion form, it's just R 1 over R minus R prime, and then plus R minus R prime dotted with R double prime divided by R minus R prime cubed. Okay, and then there are, of course, next to leading order terms that that we can evaluate. And so we go through this machinery, we plug in the extension, the expansion, and you know, we do some algebra, and we end up with the expression for phi. In this case here, phi is just ke integral of p, which is now the polarization density r prime ds prime divided by r minus r prime and minus ke, and now it's the divergence of e divided by r minus r prime dv prime. Okay. Similarly, for the vector potential, I can write km. Now that's the integral of over the surface of m, where this is the magnetization density, r prime coordinate system, cross ds divided by r minus r prime plus km the integral, and now I've got the curl of m r minus r prime d prime. Okay, so given these two expressions, we can naturally see that if I imagine that the scalar potential and the vector potential here and here are proportional to 1 over r. Okay, so what we see here effectively is that we have some surface, some effective surface charge and some effective volume charge density here and here. And similarly, for the current, we have some, surface current density, and we have some, volume or just regular current density here. So indeed, that's what we ended up writing down, such a way that we have surface density due to the polarization, just P dot n hat, and then we have some charge density here, which is the negative gradient of the polarization, and Am here is the surface charge density, which is just m cross n hat, and some charge density, which is just the curl of m. Okay. So once we've identified these, we can actually define two new fields. So that D is the displacement field, which is defined by E plus P, and then H is just 1 over mu naught B minus M. And following from these, we get new Maxwell's equations, or Maxwell's equations in matter, so that we can write the gradient of, the divergence of the rho F. In this case, this is the free charge. Okay, so not the same as this rho P, which is the induced charge density. This is really the free charge density. So it's nothing that is kind of effectively being pulled apart. No, this is really the actual charge density. And similarly, we have that the curl of A remains 0, and we have that the divergence of B is 0, and the curl of H equals to free current here. Okay. Now, given these are so-called differential form, of course, differential forms. And this is something that we extensively studied throughout this lecture course is the differential forms, but of course we do have the equivalent integral forms that we may consider as well, which are given by the integral of d dot ds equals the total free charge, integral of E dot dl group integral equals to 0, and then the B dot ds, the flux of the magnetic field, remains 0. Now we have that, H dot dl equals the total free current. These are the new integral forms. Okay, so are there any questions at this point about the treatment that we've introduced for the fields in matter? Okay, so the question is, what is the meaning of free charge? So in this case, the total charge, so rho, or charge density, is made up of free plus the polarization charge density. And so let me put it this way. Let's consider some conductor, and if I put in a field, right? If I apply a field, and let's apply it, kind of in a non-uniform way, what I'll do is I end up, kind of creating a field here so that there's some non-uniform polarization, so that there's some, charge density here, which is rho p. Of course, this sphere itself, this conducting sphere itself, could have been charged, right? And so that's the separation between free charge, which is something that you've actually kind of put into the system, versus this polarization charge, which only exists because you've introduced an external field, and so you effectively get something that is kind of a polarization charge. So for example, in Griffiths, these are typically called bound charges. So these are not things you can extract from the system, but they only exist, or they effectively exist, because you have a net polarization. So so Ling is asking what is the free current? So that would be the equivalent. Okay, so if I have I could have a current that I introduce externally, right? I could have a wire coming through, and then I have some free current. Okay? Or I have so-called bound current, which is basically what I would get if I magnetize the system. So let me just this. open up a new page to draw this out. So when I have, so for example, I've got some here, and if I introduce some non-uniform field, I get some, non-uniform polarization, and I'll introduce some polarization charge density. Similarly, for example, uh, if I have some magnetic material and I put in some magnetization, what I end up getting is, basically a current going around it here like this, which is the, more or less the magnetization current. So let's call this JM. Okay? So this would be the current that is only due to the magnetization. Once you get rid of the magnetization, you will not get this current. Whereas, consider the opposite, which is the free current or the free charge density, in which I can now, these are things that I put into the system externally, either by putting charge on this conducting sphere or by, winding a solenoid around this magnetized material. Okay? We'll see more examples of this later on, because what I want to do now, especially with this topic, is I want to show you more examples. Topic can be quite tricky, especially when you have to consider different dielectrics, different magnetized materials. So for this chapter, I will focus a little bit on giving you some examples, and we'll see more later. Okay. Anyway, by the way, thank you very much for the questions. This is good, right? This is the point of being in class live rather than listening to the recording of this. Okay, now let's go to a quick break. But in the meantime, right, let's take a 5-minute break. But in the meantime, I want you to recap for yourself what are boundary conditions. What are the boundary conditions for the electromagnetic field? Okay. And in this case, I do mean free space, because after this, we'll take a look at what are the boundary conditions when we talk about dielectrics and magnetized materials. Okay, so let's take a 5-minute break. Let's come back at 2:05, and then we'll take a look at the answers for this. But for the time being, recap for yourself what are the boundary conditions for the electromagnetic field. Okay, see you in a bit. Okay, let's get back into it. I'm sorry for the slight delay. I just got a phone call from Nigeria asking me to regarding the PhD position from Nigeria. Okay, so let's get back into it. Let's take a look. What I hope you've had time to some time to think about it. What are the boundary conditions for the electromagnetic field? Anyone want to give it a go? What about the electric field? What are the boundary conditions for the electric field? Anyone? Okay. Alex saying E above, E below is sigma divided by epsilon, epsilon naught, I presume you mean, and in the direction of the surface, right? So the parallel component is non-zero, it's discontinuous, and Yuan Manchung is saying V of philo equals 0, indeed. So that's the scalar field is continuous. Very good. Okay, excellent. So that's the electric field. What about, well, I can write it down first. So this would be of minus E O plus sigma over epsilon naught n hat, and V above minus V below equals to 0. Now, what about the magnetic field? I want to give it a go. What about the directionality, at least? Can we say something about the directionality? Okay. Alex saying B above minus B below is mu naught K cross N hat. So Alex, is this field parallel or perpendicular to the surface? Parallel. Very good. Okay. So indeed, when we look at the magnetic field, B above minus B below equals to mu naught K cross N hat. Similarly, for the vector potential, this is just a continuous thing, equals to 0. Okay, so indeed this is normal to surface, so it's discontinuous, and this here is discontinuous, it's parallel to surface. Okay, very good. So those are the those are the boundary conditions for the electromagnetic field. I just want to, just give you a bit of reassurance that if you don't know, or if you don't know how to at least derive this, let's take another look at this. But now from the perspective of our displacement field and the auxiliary field. So just to recall, okay, so let's take a look at the electric field. So remember that the D, remember that D dot ds here equals QF, right? So this would be the equivalent of Gauss's law, but now in medium. And so I could actually end up doing the exact same thing as I did when I derived the boundary conditions for just the electric field. So let's draw myself some surface over here with some thickness. This. Learn how to draw. Like this. Perfect. Okay, so if I want to look at how this would go at the interface, again, I can simply draw a Gaussian pillbox. It look like this. Okay, we'll have to go a little bit freehand. On the surface like this, with some depth. This is now below the surface. Like this, okay? And I give it some depth epsilon, and the trick is here to let epsilon go to 0. And now, because I need to do the integral over the entire surface, then all the side surfaces here, here, and this side will go to 0 because epsilon goes to 0, and the only remaining contribution is the flat surface on top and the flat surface at the bottom. If I give this A, then I could simply I simply have two contributions. One is A, right? Some area A at the top. One is some area A at the bottom. So indeed, I could take a look at here is just D. And in this case, the A is perpendicular to the, well, okay, it's the only contribution is the one normal to the surface, right? The one parallel, because of the dot product, disappears. So I have, this is the parallel above times A minus the parallel below times A equals to the total free charge now, which is A times some free charge density. Of course, all the A's can be just can be cancelled out, and so indeed I end up with now my expression being D above minus D parallel below equals to sigma F. Okay, note that there's a slight difference with respect to having whether you have the epsilon naught or not. Okay, but that has more or less to do with how we defined the D field here, the displacement field, which I've put here, is as you can see, there's the epsilon naught here that accompanies the E, but not the P. So D here is actually, has an epsilon naught difference with E. That's where this more or less comes from, right? Because if you think about it, everything has to tend to the same thing if P equals to 0. So in this case, if P equals to 0, D is just epsilon E, epsilon naught E. So if I write epsilon naught E here, I recover the same condition as I've written it down here. Okay, so that's for this for the first boundary condition. The second boundary condition is again it's the same, right? E, well, it starts with this equals to 0. So here we recover the same. Actually, let's not put this on the same page. So here E dot dl in a loop equals to 0, which is just the same as the vacuum equations. So indeed, E parallel above minus E parallel below equals to 0. Okay. Now, similarly, I could, I could do the same thing for, actually, was it? Oh, by virtue of this one here, you can also immediately see that phi above equals phi below, right? Because the boundary condition that we had for phi for the scalar potential is derived from this equation over here, this here below. And we can now move on and we can look at the B field here. So we know that for the B field, the flux is always going to 0, in which case I know that, which is the same as for vacuum. And so the boundary condition is the same. So we've got B above equals B perpendicular below. However, now for the other one, which is that H integrated around the loop equals to some surface, some vol, well, okay, some kf, some kf. Sorry, some bound. Yeah, the free one. Yes, correct. And here, what we can do the same situation as we've drawn before. So again, let's consider some surface here, some thickness here. This, like this. But instead of now using a Gaussian pillbox, what I do is I just imagine a loop going like this, like this, like this, like this, and denote this surface. Where this surface is. So if this is kind of the surface, I go around in a loop like this. So I could take H around the loop, and in this case the current is going through it like this. Right? That's the free current that goes through, and so I could take a look at this. If I now let epsilon, in this case, let's make this the height epsilon. Again, I let epsilon go to 0, so I only get this length and that length out. and I can play essentially the same trick. So here I would do the following. I get that H parallel above minus H parallel below times some L, right? Let's make this distance L. Remember, yes, you're right. This should be IF. Current should be IF. Which is in this case just the amount of current going through the surface here, and so I have that IF. Oh wait, should be KF. All right, it should be KF. Sorry. KF. It's the surface current times L. And so here again I get something that then looks like H above minus H parallel below equals to KF. Okay, now what we basically have are now a set of boundary conditions that look almost the same as they did before, but now using the free current and free charges. Yeah. So here we have the same thing, right? Here we have that D, the parallel component of D, is now dependent on the free surface charge, and we have that the auxiliary field depends on the free current, surface current. Okay, now for the other ones, they remain the same, right? So the parallel component for the magnetic field and the perpendicular component for the magnetic field and a parallel component for the electric field remain continuous. Okay, so those are the boundary conditions. Okay, so that pretty much closes everything out. Okay, we've looked at the field equations for the material in matter, and we now have considered the boundary conditions. And remember, right, whenever we solve the Poisson equation or when we solve the Laplace equations, those are the only two ingredients that we need to know. So in principle, everything is done, right? We've rewritten now, when there's a magnetization or when there's a polarization, we've written down everything. And you may say, okay, well, we're fully done that. And the situation is slightly more tricky, because the biggest caveat, the biggest uncertainty or biggest unknown in this case is, well, what is this P? And what is the magnetization, right? So given a particular external electric field or some charge, some free charge density somewhere defined, what is P and what is M? This is a very tricky question, right? Remember when I mentioned that P and N depend crucially on, you know, on quantum mechanical effects, or at least the effects associated with the material itself. So if I have a crystal, then there's a crystalline structure. And so, how can I polarize, or how can I magnetize the material given some external field? It depends on the orientation of the crystal. It depends on the exact composition of the molecules. It depends on many, many things. And in this case, one thing that I do know is that it depends on the field, right? So very generically, what I can write is that P equals to epsilon naught some chi, let's call it chi e, which is a function of the electric field times the electric field. In this case, chi e is just the electric susceptibility. Now, I'm going to put a special symbol here. I'm going to put two little underlines here. And that's the way I typically introduce the concept of a tensor. Okay. So, in this case, chi is not simply a constant. If it was, then E would be parallel to P. But no, here I've got some vector, which is, which is operated on by a rank 2 tensor, so that P could be in any direction and of any strength. This is something that I showed before in a few lectures before as well, where I would basically have that chi xx ex plus chi xy ey plus chi xz ez, and that would be the px component. Right? So the x component does not only depend on the x component of E, but also on the y component of E, and even the z component of E. So that's, writing it in the most general form. If I do that, then this problem becomes very complex. The system becomes almost so complex that it would be impossible to calculate. So let's note it down that chi e in general is a rank 2 tensor. But what I want to do now slightly differently is, okay, so there's a question from Alex. Does it mean we have a rotational matrix that rotates the direction of E? So Alex, the answer here is it's not necessarily a rotation, right? Because it could also, I don't have to just simply rotate the vector. I could also, I can also elongate the vector as I rotate it. So indeed, when chi e is in general not a constant, then yes, there will be some degree of rotation or mixing, if you will, between the x, y, and the z component, but it does not mean that it is strictly a rotation, just a pure rotation. So it could mean that I make the x component twice as contributing as the y component. Yes, you're right. There is, to some degree, there is a rotation. If you really want to be very very clear, it could be a rotation and then a translation. So Shenji is asking, what does a rank 2 tensor mean? Okay, me writing down rank 2 tensor is basically just kind of giving you the general term for this. A rank 2 tensor is basically, it's a generalization. A tensor is a generalization of a vector. So rank 2 means it has two components, whereas a vector has one component. So a vector is a rank 1 tensor. If you wanna get very mathematical, then a rank 2 tensor is something that takes in a vector. A rank 2 tensor takes in here a vector and then outputs another vector. So it operates on a vector to give you a vector. That is a rank 2 tensor. Okay, if you're curious, if you're interested in all of this kind of tensor business, I do suggest next term the relativity course, and there we're going to look very extensively at the meaning, the differential geometry meanings of tensors, in arbitrary n dimensions. Okay, but for now, it suffices to say that chi-e in general need not to be a constant. And so, technically it's a rank 2 tensor. But what it exactly is, and as Jeffrey's saying, it's not just a matrix. That is correct. But the details, I'm not gonna. It's beyond the scope of this course. So don't worry, you don't have to know that detail, because this was supposed to be a segue into into saying that we can actually consider a special class of materials which have two properties. So it is a linear material. What do I mean by linear material? That is that the rank 2 is actually replaced by some constant. Okay? So in this case, chi is just a constant. So the P polarization either points alongside with the E field or in the opposite side. So depending on chi, whether chi is a positive constant or a negative constant. Okay. But we also assume that it's a homogeneous material. In which case, chi is chi almost as a function of r is simply, again, just a constant. So it's not a rank 2 tensor, and it really is a constant throughout the entire material. So it's not like, depending on kind of your position away from the material, things will change. So it's a homogeneous. So every block that we consider is it in itself the same thing. Okay. And so that is a subclass of materials that that we will consider, and this is typically abbreviated to LIH in some books. And so again, this is just some nomenclature. So if they talk about LIH dielectric, then the assumption is just that it's a linear material and that it's a homogeneous material. Now, similarly, I could also consider the magnetized version, and so in which case, I have M equals some chi M, which is a function of H times H, where in this case, this chi M is now the magnetic susceptibility. Okay. And again, we can make this explicit assumption that chi M of H is just some chi M for linear and homogeneous materials. Now, this subclass of materials has two things, right? One, it's quite prevalent. For most common materials, this description is a good enough description. Okay, so most materials do not exhibit very strange behavior. And so here, what we generally, this encompasses paramagnetic and diamagnetic materials. And so this is one, a good approximation, but two, also it is also one that allows us to make calculations to find solutions to, to the field equations in a relatively simple manner. So that's why we consider these so-called linear and homogeneous materials. Okay, let's take a quick break here, and let's after the break, let's take a look at how, given these linear materials, how do the equations change, and how do the equation change, and also let's take some specific examples. Let's take a look at specific examples for how do we calculate the different fields outside dielectrics and magnetic materials. Okay, let's take another 5-minute break. So let's come back at 5:39. Let's make it 5:40. Okay, see you guys in a bit. Okay, welcome back. Let's take a look at the last part of today's lecture, where we're going to continue considering these linear and homogeneous materials, and then we're going to take a look at a few examples as well. Okay, so the thing that we just introduced just now is saying that, you know, in a special case of special materials, so it's linear and homogeneous, so chi e are now, you know, considered to be linear and homogeneous materials. So this chi e is simply a constant. Okay, in which case it means that P and E are pointing in the same or anti-parallel directions. Similarly, we can write this for chi m. Okay? So which case again m is the same, is in the same direction as the auxiliary field. So what does this mean for the displacement field, and what does this mean for the auxiliary field? Let's take a look there. So we can first define so-called just the epsilon. So define epsilon equals epsilon naught 1 plus chi e, and mu naught 1 plus chi m. And so basically, what we started off with saying that when we have a some dielectric is that, you know, instead of this epsilon naught, we basically get an effective epsilon, which here we've defined it as the epsilon naught 1 plus chi e or mu naught 1 plus chi m. The reason is because then the equations become fairly straightforward. So let's take a look at the displacement field. Displacement field is given by d equals epsilon naught e plus p. Okay. Now let's go back here. Now we have epsilon naught chi e e. So in this case, what do we have? We have that epsilon naught e plus epsilon naught chi e. This here is now epsilon naught e 1 plus chi e. It's the same as just epsilon e. Okay. So indeed, we can see that the displacement field is just proportional to the electric field. And the constant of proportionality, instead of it being epsilon naught, now is just some epsilon, which is dependent on the electric susceptibility. Now, similarly, we can do the same thing for the auxiliary field. Auxiliary field is given by H equals 1 over mu naught B minus chi m m here. Oops, no, sorry. That is a boo-boo. That is m. Okay. But now, again, for linear materials, I know that m is just related to h. Following way, so I can now write mu naught b minus chi m h. And I can simply rewrite this again in such a way that I get 1 plus chi m h equals 1 over mu naught b, or in other words, h 1 over mu naught 1 plus chi m equals to 1 over mu b. Okay, so for these linear materials, the relationship between B and H, or between E and D, is simply a constant of proportionality, in which case instead of 1 over mu naught, I get 1 over mu, or instead of 1 over epsilon naught, or sorry, instead of epsilon naught, I get epsilon. So this makes it simple because now I, in principle, don't need to consider the exact form of P, right? Because I know it's proportional to E. And I want to stress that this is only in the case of these linear and homogeneous materials. If chi E is some generic rank 2 tensor, then it depends on the detail of this tensor before I know what P is given a certain E. Generally, this is a very difficult calculation to do. For these linear materials, I have these nice and linear relationships, and then I can do the computations relatively easily. Okay, let's take a look at these linear materials, and let's see if we can do some examples. Right? Let's see if we can come up with some examples and test our knowledge in this case. Okay, so the first example that I want you to consider is I have a disk here, and this is some linear and homogeneous material, dielectric material, and I'm putting some external field E naught in here. Okay. I can consider the thickness of this to go to 0, right? So it's just a disk. And then the question is, okay, well, what is the total electric field? What is the displacement field? What is the polarization field? And what are the induced charge density and the induced surface charge densities? And in this case, you may assume that you know, so you know chi E. Okay, so I'm going to give you 2 minutes to think about, okay, what it is that how would you calculate all of these factors over here? What are the steps that you need to take? Okay, I'll give you 2 minutes. Think about it, and we'll come back in a second. And let me put this. Oh, okay. There are 2 slides that you need to know. There's this slide and this slide. Okay, let's take a look at this specific example. So again, we have a disk with a linear and homogeneous dielectric, and I put it in some external field E0, which is perpendicular to this disk. So what would be how to calculate E, the total electric field inside this material? What's the displacement field? What is the polarization field, and what are the induced charges? So the first thing that we want to identify the things that we do know. Okay? So one thing that we know is that the electric field outside is easier. That means we also know what is the displacement field outside of the material, outside the disk. So who knows what is the displacement field outside this outside the disk? Tell me that. You remember what the formula is for the displacement field? Discussed this a few slides ago. How's the displacement field related to the electric field? D equals epsilon E. Okay, very good. Indeed, right? Because we know that D outside is epsilon naught E outside plus P outside. P outside equals to 0, because in this case we're in vacuum. So in vacuum, okay, and so indeed D outside equals to D. Sorry, it's just equals to epsilon naught 0. Okay, very good. That's step number 1, right? That's the easiest thing. I just know that, okay, on the outside, I have my material. Okay, sorry, I have no material. Okay, so now we need to look at the we need to look at, okay, well, how do I evaluate this on the outside? Well, I have some linear dielectric, which I should, okay, otherwise neutral. Okay, so no free charges. Okay, but even if there were free charges, the next step would then to be considered, what is the boundary condition, right? What is the relationship between the D outside and the D inside? So if I look at this slide over here, this slide over here, so indeed I have that the perpendicular component of D above minus the D perpendicular component below equals sigma F. So that's the free surface charge. In this case, we have a otherwise neutral dielectric material, so we don't have any external charges that we put here. So what do I know? So from the boundary condition of D perpendicular above minus D perpendicular below equals the free surface charge equals to 0. So D perpendicular above equals D perpendicular below. So in this case, what do I know about inside and outside? What do I know about the displacement field? So the displacement field in this case should be continuous. So displacement field, because there's no free surface charge, is continuous. So I know that the D on the inside is the same as a D on the outside. Which I know the D on the outside is just epsilon naught E naught. Epsilon naught E naught. Okay, so now I know what the displacement field inside is. Okay, so how do I now go to what is the electric field on the inside? I've told you that this is a linear material. And in this case, if it's a linear material, I know I can relate D simply to E using the using epsilon, where epsilon is here given here. It's epsilon naught 1 plus chi E. It's just the electric susceptibility. So I also know that D on the inside is epsilon E on the inside. So in this case, I pull these together, I have that the electric field inside is the displacement field inside divided by epsilon, which is the same as which is the same as d in. D in is epsilon naught 0. So indeed we get epsilon naught over epsilon 0. In this case, we know that everything is normal to the surface, so I'm not explicitly putting the arrows here. If you will, if you want to write it in terms of the susceptibility, we can simply follow this. And so we could get rid of the epsilon naught and just write 1 plus chi E. Okay? Or just leave it like this. Some textbooks actually refer to this as epsilon R. It's the relative permittivity, I think it's called, or anyway, it has some term like this. But I don't know, it's up to you. I always get confused the more of these epsilons and stuff I introduce. But you know, it's up to you. But that still means that I know now what the E inside is. Okay, so if I take a look at the question, I know what E is inside is now, and I know what D inside is. So okay, well in that case, let's take a look at the next thing. What is P? What is now the polarization inside? Well, we started off, right, for any general material, polarization is given by P equals to epsilon naught chi E of E. So in this case, P in is just epsilon naught chi E in. which I have it as here. So here I can write epsilon naught c squared IE over epsilon E0. Let's see if that's correct. P is correct. Okay, of course you can rewrite this again. If I expand this E, if I substitute this, which would be epsilon naught 1 plus chi E. So I think I did this correctly. Right, this is epsilon naught chi E 1 plus chi E. Oh, okay. And then finally, we can write the bound charges are then, the rho P. It's just the negative of the divergence of P. Okay, in this case, because P is uniform, it's uniform because E naught is uniform, so that is just 0. Okay, uniform. And then here we've got sigma B, which is just P dotted with N. It's just a perpendicular component. And so it's just, plus or minus P, depending on whether you take the top part of P, of this disk, or the bottom part of this disk. Okay, so I should write this. Because I know E in this case is just in the direction of naught. Okay? So depending on which surface you take, that is either the positive or the negative charges. Okay, so I hope you kind of see this logic flow, right? That where we're going towards. And the crucial thing is identifying what it is that you know. Right? In this case, I know that I have an external field, and so I know what the external D field is. I know how D goes across the top and the bottom of the interface. So outside, which is what I know it's continuous because there's no free charge. And so, I know that the D inside is the same, and otherwise it is completely linear and homogeneous. So I can calculate the E inside, which gives me the P inside, and once I know the P inside, I know how to calculate the charges, the bound charges. Okay. Now let's take a look at specifically what happens inside the material. And again, for that um, we can take a look at a very specific example. So here, let's take a look at a more specific example, and let's just draw the actual. Let's enlarge this now. So let's give it some thickness, and we can actually take a look at what happens inside. So here I have that there's some positive charges. So here, and it's got some negative charges here, where in this case P is lined up like this. Okay. And so what we said before, we've got sigma B here, which is plus P, which is the magnitude of P. And then at the bottom, sigma B equals minus P at the bottom. Okay, Now, so the what happens inside the material now, and that's something that I can also explicitly calculate, right? Because this is pretty much just a a parallel plate capacitor in this case. And so I could also explicitly calculate the electric field on the inside and on the outside. So this is a result from 2041, but can anyone tell me what is the electric field of an infinite plate with some surface charge density? Does anyone know? Just a sheet, an infinitely stretched sheet with some surface charge density. For an infinitely charged plate, it's sigma over epsilon naught. Yeah, I think there should be a 2. Okay, good. Anyway, Harry, Jeffrey, Shunchi, yes, that is the expression I was looking for. So I know that the top plate here, I know that the electric field here generated by the top plate is just, I'll just call this the top plate. Let's just call it top. The top plate is just over 2 epsilon naught. And then in case of the bottom plate is just minus p over 2 epsilon naught. Right? In this case, because sigma b equals p, and sigma b equals minus p. Okay, so now we are in a position to see, okay, what's going on with the electric field? Like, what is the field caused by the polarization? So if I look at the outside, if I take a point outside, well, we know what the electric field outside a parallel capacitor plates are, which is just, I add these two things up, I simply get 0. Inside, of course, because one surface is defined in this direction and one surface is defined in this direction. So on the inside, I basically have that the E, due to just the polarization, equals P over epsilon naught. On the outside is it's just 0. 0. Okay. Now that is only the electric field due to the polarization. The total electric field, which is basically what we considered in when we did the calculations here, is now the total electric field So now E equals E naught plus E. Okay. In this case, I have to do the sign correctly, which is in the opposite side of epsilon naught. So here I get naught minus chi E, right? Because P in this case is just chi E, epsilon naught E. And so I can now write the total E is just E naught 1 plus chi E. So if we take a look at this, so I have some external naught. Okay, I'm creating plus and minus charge on each of these, on each side of the surface, and I end up with the total electric field inside being the electric field outside plus 1 plus chi E. Now, generally, for dielectric materials, generally chi E is bigger than 0, okay, because the polarization tends to be in the same direction as the electric field. And we saw that before. We we dipole separation of a molecule. So this is bigger than 0 in such a way that is smaller than E0. Okay. So when we talk about dielectric, what happens is that there is some degree of shielding. The electric field inside is now, because of these induced charges, is going to be less than the field outside. Okay, if you will, we create this setup over here, right? We push some charges to the top, we push some charges to the bottom in such a way that we create a field that opposes this external field, and therefore E is smaller than E0. So if you will, what we get is some effective shielding. Yet, the setup is done in a way that we effectively shield away some of the influence of the outside electric field. Now we could even take it to the most extreme case. So for conductors, chi E goes to infinity. And so in that case, E goes to 0. Okay. So when it's completely ideally able to mobilize charges, right? There's an infinite reservoir of charges. Then I could create a setup in such a way that I identically cancel the field on the inside. So we can kind of see that the conductor, the ideal conductor, is just the limit of a dielectric, of a linear dielectric. Okay, so that's just an example of how to do this whole stacking up boundary conditions so that you're able to calculate on the what the fields are on the inside. Okay. This pretty much ends today's lecture. Next lecture, we're going to take a look at an example for the magnetic field, auxiliary field. We're going to take a look at a little bit of a special material also for for magnetizable materials. In that case, ferromagnets. And then we're going to take a look at more examples. Right? Like I said, the theory behind all of this is relatively similar to just the field equations in vacuum, right? Just some modifications. But I think it's worth to take a look at a few more examples of how to calculate the displacement field, the electric fields, the auxiliary fields, and the magnetic fields on the outside. Okay, that's it for today. Again, as a reminder, the next lecture, we're going to do the course evaluation. So, a link will be provided, and I'll give you some time during the lecture to fill in the form. And then we're going to take a look at more examples of how to deal with scenarios, electromagnetic fields in matter. Okay, let's end this here, and let's see if there are any questions. Going once, going twice. In that case, let me stop the recording.